Hello everyone, I'm Eiichiro Kokubo. I'm from National Astronomical Observatory of Japan and also University of Tokyo. Today I talk about the formation of terrestrial planets. So we have already learned from Nadal's talk the basic physics behind the planet formation. So then I like to focus on the dynamical models, so which is more relevant to the terrestrial planet formation in the solar system. And before starting my talk, I'd like to introduce some recent review papers. So if you are interested in some specific topics in my talk, please refer to these papers. So these are about the formation of terrestrial planets, not only in the solar system, but in exoplanetary systems too. So you can find maybe this view graph on the net, right? Later this conference. Okay, so this is the outline of my talk. So let me start my talk with introducing some important properties of terrestrial planets in the solar system. So then I like to explain the basics of standard formation scenario, or maybe conventional formation scenario. We have already heard a lot about this from Nadal's talk. And then we move on to each important process. First one is planetesimal formation, and then planetesimal accretion, so coagulation. And then the last stage of the terrestrial planet formation, at least in the solar system, is considered as a giant impact stage. So where relatively big bodies collide with one another to complete the terrestrial planets. So which is very important because this stage, all the orbital properties and spin parameters are determined. So which is very related to the habitability, right? And then after introducing the standard scenario, I like to show some examples of the extension of the standard scenario. So including, we have already seen this Grand Tack model. And then we summarize my talk. And then at last, I like to show you some animations, photographic animations rendered from our group's N-body simulations. Okay. So terrestrial planets, we already know that. So Mercury, Venus, Earth, and Mars are terrestrial planets, right? And they are also called as rocky planets. So they reside in the inner part of the planetary systems in the solar system. So ranging from 0.4 to 1.4 AU. And the mass ranges about 0.1 to 1 Earth mass. And this on the right, so this is the cross-section of the typical terrestrial planet. So very roughly speaking, it consists of two layers. So in the center, we have the core, consisting of mainly of iron and maybe some nickel and some light elements. And surrounding it is this mantle. So mainly this is silicates. So, and this rock to iron or mantle to core ratio in mass is different from planet to planet. For example, for the Earth, the core mass is about 30% of the total mass. But for Mercury, I think the core mass is now estimated to be as maybe about 70%. So actually, the Mercury is not a rocky planet, it's an iron planet. And then this figure shows the mass against the semi-major axis. So by looking at this figure, what do you think about the mass distribution of terrestrial planets in the solar system? So we notice, so from this plot, maybe there are two populations, right? So the bigger ones and then smaller ones. So this is Venus and Earth, and this is Mercury and Mars. So it seems there are two populations. So why? So we like to explain this during the course of formation, right? And this figure shows the orbital elements. So semi-major axis, and black points are eccentricities, and white ones are inclinations. So Mercury, Venus, Earth, Mars. So very roughly speaking, so inclination here, the unit is radian, not degree. So all of them are smaller than, say, 0.1. So that means the terrestrial planet's orbits are nearly circular, and also the mutual inclination is very small, so coplanar. So in this figure, the inclination is measured from the mean orbital plane of the solar system, called as Laplace plane. So they're very, the orbits are very neat, well organized. Okay. And this figure shows you the spin parameters. So the horizontal axis is the period in the unit of days, and the vertical axis is obliquity. Obliquity is the inclination between the spin axis and orbit normal. So as you know, the Earth has 23.4 degrees. So from this figure, so this is, I think, Earth and Mars. And this is Mercury, right? So they are prograde. They have prograde spin. So prograde here spin means the spin direction is the same as orbit direction. But Venus has retrograde spin. And the period is larger than 200 days. So it's almost, not spinning. So from this figure, we can say, well, it's a bit difficult to say quantitatively the probabilities, but at least we can say it's very diverse, right? So this probability also we like to explain during the course of formation. Let me recap briefly the important probabilities when we consider the origin of terrestrial planets. So they have bimodal mass distribution, so large planets and small planets, right? And orbits, the semi-major axis, in the inner part of the solar system. So I call here the localization. So we don't have terrestrial planets inside the 0.4 AU and outside 1.5 AU. So it's very limited. The range is very limited. And large planets are inside, I mean Venus and Earth are inside this distribution, and Mercury and Mars are outside, right? And all planets have relatively small eccentricities and inclinations. Especially Venus and Earth, eccentricity and inclinations are small. And spin obliquity is very diverse, right? From 0 to 180. And so period ranges from about 1 day and to 100 days, the order here. So, but please note, the effective spin period of the Earth-Moon system, if the angular momentum of the Earth-Moon system is just added to one Earth, so the Earth spin may have this period of 4-hour spin. It's very fast spin. So the Earth-Moon system has relatively large angular momentum corresponding to this 4-hour spin period. And compositions, so they're also different. So especially Mercury is different from others. So these are important properties of terrestrial planets. So we like to explain. And of course, so we all here are interested in the habitability of planets. And so because maybe tomorrow or maybe in this late afternoon, we discuss about the habitability. But so habitability is generally defined as this, right? So habitability is like stable existence of large-scale surface liquid water, because our type of life needs liquid water during at least some part of our life cycle. And this habitability, the existence of liquid water, can be translated into some dynamical conditions of planets. So mass, orbit, and also spin parameters. All these, matters when we consider the habitability. But the classical habitability only, considers the semi-major axis. But eccentricity, we have already these papers discussing about the effect of eccentricity, obliquity, and spin. So these dynamical properties are very important when we consider the habitability, as we know. Okay, so now let me introduce you the standard formation scenario. But actually, we have already heard from Nadal. So let me briefly repeat that. So behind this standard formation scenario, there are two hypotheses. So the first one is disk hypothesis. So we consider that a planetary system is formed from a light circumstellar disk. It's called protoplanetary disk, and that is a byproduct of star formation. And this disk has the same composition as the host star. Then second hypothesis is called the planetesimal hypothesis. So from only the dust of the disk, so planetesimals are first formed somehow. And solid planets, like terrestrial planets and ice giants, are formed by accretion of these planetesimals. And to form gas giants like Jupiter and Saturn, so first, the relatively large solid planets, cores, are formed by accretion of planetesimals. And then it becomes big enough to capture gas from protoplanetary disk by its self-gravity. So then the formation of the gas giants are kind of two-step. And by this process, so first we form core, then core accretes gas. So this model is also called core accretion model or core nucleated accretion model. And these models or scenarios are developed independently by Safronov and Hayashi's group, and also some Pollack et al. And I bring here this very, very rare, important picture showing this is Hayashi. So astrophysics major students, you may know the Hayashi phase, right, for star formation. And also for the planetary people, we know Hayashi disk, right? So this is Hayashi, and this is Safronov from the Soviet Union. So and Hayashi and Safronov, when I was first see this picture, I was very, kind of surprised and also moved. So these two giants, stand next to each other. But well, you don't have to remember, but it's a good, the picture. Okay, so what is this standard formation scenario? So this is a cartoon describing it. So this is the edge-on view of the protoplanetary disk. The formation scenario consists of 3 stages or 3 acts. The first one is the formation of planetesimals from dust. And the second one is formation of protoplanets from planetesimals. But this protoplanets is also called embryos. So embryos and protoplanets in my talk are the same. And the last stage is formation of terrestrial planets from protoplanets. And this stage is known as the giant impact stage. So we'll look through all stages. So from Inga's talk, we already learned about the latest picture of the protoplanetary disk. But for the standard disk model, we just assume this very simple protoplanetary disk. So the size is about the same size of the planetary region. So in the solar system case, so it's around maybe radius is 30 AU. And mass is about 1% of the sun. And the composition is same as the sun, which means the dust to gas ratio is only 1%, right? But also we have already know from maybe Inga's and also Nadal's talk about this snow line. So snow line is the border of the composition of dust component. So the definition of snow line is, for the H2O snow line, it's the distance from the central star to the point where the disk temperature is about 170 K, so which is the H2O condensation temperature under very low pressure, like protoplanetary disks. And so if the disk is optically thin, I mean here the main heat source of the disk is the central star. So in that case, the snow line is around 3 AU. And inside 3AU, the dust is almost rocky. And outside the snow line is icy. Of course, this part, we have rocky dust, but assuming the solar abundance. So H2O is about 4 times more here, beyond the snow line. So then we say just main component of dust is icy outside the snow line. And this snow line sets the basic boundary between rocky and icy bodies. Well, of course, we know they migrate, but the formation, so this snow line is the boundary, right? So now we come to this planetesimal formation part. So this is, I think, now the most difficult stage of planet formation. So let me start with introducing the 2 classical models. The first one is very simple, just pairwise coagulation of dust grains, right? But as we have already learned from Nadal, so these compact dust grains may fall onto the central star before it grows to the size of planetesimals. So it's called a radial drift barrier. So then to solve this problem, the people are working on the standard formation scenario. They found this mechanism called gravitational instability of a dust layer. So here, so this is a part of protoplanetary disk, and it consists of gas and dust. So dust settles toward the mid-plane. And once the density of the dust layer becomes higher than the Roche density or some critical density, then the dust layer becomes gravitationally unstable to fragment. Then these fragments can shrink to finally become planetesimals. But also the second classical model has now we understand as difficulty. Because to this mechanism to operate, the protoplanetary disk, I mean gas component, should be very calm. So otherwise, the dust components cannot settle toward the mid-plane. But from the observations, we can estimate the strength of the turbulence of the protoplanetary disk. And now I think we agreed that, so maybe it's very difficult for this kind of mechanism, because this protoplanetary gas is a little bit too turbulent. So then how can we form planetesimals? So and then I list up recent models, 3 recent models. The first one is streaming instability. So I'm sorry, I don't have time to go into details, but this is a kind of 2-component fluid instability. So it's like a traffic jam effect. So this streaming instability is as particles form clumps, and where we can expect the gravitational instability from planetesimals. And the second one is secular gravitational instability, so which I worked on. So this is not the dynamical gravitational instability we talked about here, but the secular gravitational instability, so which occurs on a time scale of energy dissipation. So in this case, the dust component's kinematic energy is dissipated by gas friction. So on this time scale, just very gradually, the dust can settle toward the midline, but on a longer time scale. So this is also one possibility. And the third one is pairwise coagulation of porous dust aggregates. So here, this porous is different from the classical one. So classical one, I put here compact. So what is this porous dust aggregate model? So we also call the fluffy dust model. I'm sorry, it's maybe hard to see. So we have already heard from Nadal that, so these days we think, when dust aggregates grow, so by pairwise coagulations, it's very hard to form very compact, high density particles. But like this kind of aggregate with fractal dimension around 2 are formed by pairwise coagulation. Let me show you this movie. So just pairwise coagulations of equal number of monomers. And what we have already found is the collisional compaction or collisional compression is not effective enough to form very compact grains. So now we think the pairwise coagulation of those grains leads to formation of this kind of fluffy, porous, low density aggregates. Right? And then, okay, so then, so this figure shows the pathway of growth of dust aggregates, fluffy dust aggregates, starting from a monomer, right? So by this growth, the density becomes low and low as they grow. But then this gas compression, I mean the compression by round pressure, and also self-gravity forms, and so they found the path avoiding the radial drift barrier. So along this line, so the dust aggregates can grow, avoiding the falling down onto the central star. So, and also, we studied this stage in detail, the dynamics of dust aggregates, to found, so this is the same, the density mass plane, and this is the growth of dust aggregates. And here, the self-gravity compression is effective. So by this evolution, the dust aggregates that inevitably hit this Q equals less than 2 area. So this here, Q is the 2 more as Q. Maybe astrophysics students know that. So this is the indicator of the stability of the disk system. So if Q is smaller than 2, the disk is gravitationally unstable against the non-axisymmetric perturbation. So then what we found is, so at this stage, so this kind of thing happens. So this is the simulation of that stage. So we are looking at some part of the protoplanet disk, face on. So they're the fluffy dust aggregates. But then the layer becomes dense enough. So first there's some inclined denser area are formed, and then it fragments to form planetesimals. But please remember, I'm not saying this is the mode of planetesimal formation. So because this animation is very persuasive, but this kind of thing can happen under some disk conditions. So this is a kind of revival of the classical gravitational instability model, but with fluffy dust aggregates. So with compact dust aggregates, we cannot expect that. But with fluffy dust aggregates, we can have this. Okay, but as well, already Nadal talked about, but somehow we think the planetesimals are formed. Because, well, from the crater records in the early solar system, we now know there are many small bodies in the solar system. And also the comets. So the comet sizes are all very similar, around 10 kilometers, right? So these are maybe residuals of planetesimals. So for the later use, we introduce this kind of planetesimal system now. So if the gravitational instability takes place, then we can estimate the mass of the planetesimals from the critical wavelengths of the instability, so which is about 10 to the 18 kilogram. So assuming the maybe I forgot 2 to 3 gram per cc the density, so the size is about kilometer. And for the later use, we introduced this surface density distribution of planetesimals by this power law formula. So here sigma 1 is the surface density of 1 AU, and alpha is the radial exponent. So this Hayashi's disk is about, sigma 1 is about 10 and alpha is 3/2. Okay, so now we have planetesimals, and then next what happens? So before going into the planetesimal accretion, let me introduce some basic concepts important to planetesimal accretion. The first one is random velocity. So this is the deviation velocity from a non-inclined circular orbit given by this equation. So here, E is the eccentricity, I is the inclination in radian, and Vk is the Keplerian circular velocity. And this random velocity increases by gravitational scattering among planetesimals on average, right? And so during this growth of planetesimals, there's always some equilibrium random velocity where the effects of gravitational scattering, so which increases the random energy, random velocity, and also the gas drag, which dumps the eccentricity and inclination, balance. So under this equilibrium random velocity, planetesimal accretion proceeds. Then the next important thing is Hill or Roche or tidal, or sometimes called Jacobi radius. And so kindly Nadal already introduced this in his talk, but this is the radius of the potential well of an orbiting body, right? So given by this equation. So where here, so m is the mass of this orbiting body, and mc is the mass of the central object, and a is the semi-major axis. So this is the kind of gravitational reach of an orbiting body. So, and I use these terms later. Okay, so now let us consider the growth modes of planetesimals. So suppose we have now two planetesimals with mass m1 and m2. So maybe initially m1 is larger than m2, let's assume. And the time evolution of this ratio is given by this formula, right? Just I expanded. And from this equation, we know, so it is this relative growth rate that governs the growth mode. So now we assume this relative growth rate is proportional to some power of mass, P. So if P is negative, so if this is the decreased function of the mass of this growing body, so if initially m1 is larger than m2, then the right-hand side of this equation becomes negative, right? So the mass ratio tends to be unity. So in other words, they all grow equally. So this mode is called orderly growth. But if this is the increased function of m, and m1 is initially larger than m2, then this right-hand side is positive. Then mass ratio increases. So this mode is called runaway growth. And around maybe late 80s and 90s, there was some discussion on the growth mode of planetesimals. And we now know from the n-body simulations that the growth mode is at least initially runaway growth. But before showing that, let me introduce the growth rate. to understand the physics behind the growth mode. So now suppose, so this planetesimal with large M is growing, and this is embedded in a swarm of small planetesimals with mass small m. And this is the growth rate, right? And this is the cross-section, for collisional cross-section, taking into account the effect of gravitational focusing. So this part, pi r squared 1, is just a geometrical cross-section, right? But now the planetesimal is, the self-gravity is effective. So then the planetesimal can gather the planetesimals, which is outside this geometrical cross-section. So this is called Safronov number. So this is the effect of gravitational focusing, and this is actually larger than unity, and this is dominant. This term is dominant. And using these reasonable relations, this can be reduced to this form. So this relative growth rate is proportional to m to 1/3 times v minus 2, v to the minus 2. So then from this form, we can understand this. It is this random velocity, right? Deviation velocity from the circular non-inclined orbit that controls the growth mode and also the time scale. So to understand this random velocity it's very important. So, and I have already told you that initially the growth mode of planetesimals is runaway growth. So, which is clearly shown by this experiment. And this is semi-major axis eccentricity. So this is the result of n-body simulation. And initially, all planetesimals have equal mass. But this is 10 to 100,000 years and 200,000 A. So you can see this one body growing very fast. So what's happening here is this. So here, so the random velocity of these small planetesimals is independent of the mass of this growing body. So V random is not the function of the large M, mass of this one. So in this case, so V random is independent of M. So then we have this positive dependence of the relative growth rate on mass. So which shows that growth mode is runaway. So we can also say in this way, at least on the linear stage, so where the back reaction of this growing body to the field planetesimal is negligible, we can have this runaway growth. And this figure shows the mass distribution for the same simulation like this one. So this is mass, and this is the cumulative number of planetesimals. So this is initially, all the planetesimals have this mass. And so after we started simulations, it relaxes to some power distribution. So there's the power exponent is given by this. And at 2 times 10 to the 5 years, so which is this solid line, the mass distribution consists of two parts. This continuous power law part, and also one runaway body detached from this continuous distribution. So this is the runaway growth of planetesimals. So then the question here is, can we form the Earth just by runaway growth? But we can't. The runaway growth stalls inevitably. So then what happens is this mode. So we call oligarchic growth. So this is semi-major axis and eccentricity. And initially, all planetesimals have equal mass. And this is time in year. So we have runaway growing body right here. But at some point, they stop growing. And then they try to keep some certain orbital separation So orbital separation is difference in a semi-major axis. So if we have 4 planets, Mercury, Venus, Earth, and Mars, so then it's okay, we can reproduce the solar system. But instead of 4 planets, we have 15 embryos here. So let me explain what's happening here. So first, so here we have the slowdown of runaway growth. So once this runaway growing body, these large bodies, mass exceeds critical mass, so which is about 100 times the mass of the field planetesimals, then this runaway growing body can very effectively scatter the surrounding planetesimals to increase the random velocity of planetesimals around it. In that case, we know the random velocity of surrounding planetesimals become dependent on, Hugh radius, so linearly Hugh radius, proportional to Hugh radius, and the Hugh radius has this dependence. So plug in this relation to this random velocity, we have this negative dependence. So then the growth mode shifts from runaway to orderly. So that's why among runaway growing bodies, embryos, we don't see runaway, but they all have similar masses. So because of this slowdown of runaway growth. And during this formation, so the growth, 2 adjacent protoplanets scatter. And by this gravitational scattering, they exchange angular momentum to expand their orbital separation. And so from this numerical experiments, we now know the typical orbital separation on this stage is about 10 Hugh radius. So that's why, so on this stage, so we cannot form 4 terrestrial planets, but maybe 15 Mars-sized embryos. And they are stable. I mean, orbitally stable. So we cannot have any more collisions on this stage. So we can analytically estimate the final mass of embryos, the protoplanets, by assuming in situ formation here with no radial migration of planet building materials, and also the 100% accretion efficiency. So we can use all the materials here to form embryos. So then this isolation mass is estimated by using the disk parameters. The sigma 1 is the surface density at 1AU, and alpha is the radial exponent of the planetesimal disk. We have introduced in the planetesimal formation section, right? And B is the orbital separation between 2 adjacent protoplanets. So you don't have to remember this formula, but it's about the Mars mass, right, at 1AU. So it's much smaller than the Earth. And the growth time also we can estimate using this equation. But let me show you by this figure about the mass of the embryos here. So together with the Mercury, Venus, Earth, and Mars masses, right? So for the standard protoplanetary disk for the solar system formation model, so where sigma 1 is 10 and alpha is 3 halves, and we have this isolation mass. So which is far smaller than the masses of Venus and Earth, but it's as high as those of Mercury and Mars, right? So from this figure, we infer, so to complete large planets, we need more collisions between embryos. But maybe Mercury and Mars are leftover embryos, protoplanets. So that's why there are two populations. But is it really true? So let's test it. So far, from dust, planetesimal, and then protoplanets or embryos we have, right? Then the last stage of terrestrial planet formation is giant impact stage. And I said the protoplanets formed by oligarchic growth is stable. Yes, it's stable. If there's disk gas, because this gas can dump the eccentricities and inclinations of embryos. But if gas disk disperses, then through gravitational scattering, the embryos build up the eccentricities and inclinations, and finally becomes orbitally unstable. So from the observation, we know the disk lifetime is maybe less than 10 to the 7 years, right? And after this time scale, so then the system becomes gas-free. And then from the numerical experiments, we know empirically that so the time scale given by this equation, so this semi-log dependence, the system becomes unstable. So let me show you this figure. So this is this orbital separation of embryos in the unit of Hill radius. And this is the time scale for the system to be orbitally unstable. And then, so just one, increase in Hill radius leads to one order of magnitude longer time scale for instability. So this semi-log is dependence. So many people have been working to understand physically why we have this dependence, but no one has succeeded. So maybe if you are good at some maybe chaos or something like that, so you can try it to solve why we have this dependence for the instability time scale. But anyway, after this time scale, the system becomes unstable, and we can have giant impacts, so collisions between embryos. And this is an example of the N-body simulations of the giant impact stage. But let me first show you some examples. So this is a SPH simulation of impact. So this case, two embryos merge after a collision. So the energy dissipation by first contact is good, large enough for the two bodies to become one body, right? But sometimes, if the impact parameter is not small enough, it just hit and run. So in my N-body simulations, so we derived the condition for the merging of embryos as a function of impact parameters and the mass ratio of two bodies. And from the numerical SPH collision simulations, we derived the conditions, and we use it in N-body simulations. And let's see the orbital then evolution. So please remember, so Nadal's talk, so he pointed out a very important thing. So because this system is chaotic in nature, so few body problem, right? So we cannot say, if, for example, the evolution of this system leads to a very similar system to the solar system, so we can learn what? But we can do these kind of simulations many times, and we should analyze the system evolution, so statistically, right? But I'm a bit hesitant to show you the very successful case first. So this is semi-major axis eccentricity. So then, starting from the protoplanets formed by oligarchic growth, then after gas disk dispersal, So the system becomes unstable on the time scale we've shown, we have seen. And in this case, I'm sorry for that. This is like solar system. But I learned hundreds of these runs, right? And what we found is that I derived some scaling laws, right? The mass distribution about, right? How the final mass or final orbital elements depends on the initial polar planet's properties. But let's see the same run, but in a different way. So here we have the sun here and embryos almost on circular orbits. And then we remove the gas component and then restart the simulation here. So you can see sometimes orbits cross, right? And they collide. And I like these animations because it's very easy to show you the very important property of this stage. So the giant impact continues until the system becomes stable. So what is this stable configuration? So which is like this, right? So in this configurations, two adjacent planets are well separated. The gravitational interaction is weak. Then they cannot make more collisions. So what we can say here is, so by this process, so the nearly circular orbit is inevitably formed. Otherwise, the system is unstable, right? So that's partially a reason of the coplanarity and also the near circular orbits of the terrestrial planets in the solar system. So, and these are some basic, okay, so then this is the similar simulations, but different runs from the animations we have just seen. But so doing many simulations of this kind, so we derived some scaling laws about the terrestrial planets. For example, the mass of the largest and second largest planets have this relation to the total mass of the embryos. And mean orbital eccentricities and inclinations are 0.1, so which is higher than the solar system's terrestrial planets. And the growth time scale is about 10 to 8 years. And let's now look at the spin parameters. So in my antibody simulations, I follow the spin evolution of planets. So this figure shows the spin angular velocity against the mass of the planets. And here, this dotted line is this critical this critical spin angular velocity for rotational instability. So the planet cannot spin faster than this. And if the spin velocity exceeds this one, then this body fragment. So what we found is then the mean spin angular velocity is about the 70% of this critical angular velocity, right? This one. And it's independent of the mass of the planet. Because the inertia moment and also the spin angular momentum cancels out the dependence on the mass. And the effective spin angular velocity of the Earth-Moon system is 1.5 radian per hour, 1.5 radian per hour. And Earth mass is 1 Earth mass, right? Here like this. So maybe the present Earth mass system is reasonably in the 1 sigma of the result of these simulations. But very interesting result found is this one. So this one, this figure shows the obliquity distribution. So this is obliquity, and this is the normalized cumulative distribution of obliquity. So remember, the obliquity is the inclination of the spin axis from the orbit normal, right? So the Earth's obliquity is 23.4. So this solid line is the result of the n-body simulations, and this dotted line is the isotropic distribution. So isotropic. So here, isotropic means, that the direction of spin axis is equally possible for all the directions. So which is the natural outcome of the giant impacts. Why? Because during this giant impact stage, the scale height, so the vertical excursion of the protoplanets, is much higher, actually, than the physical size of embryos, protoplanets. So the collisions, giant impacts, are fully three-dimensional. It's almost random, right? And also random. So which leads to this isotropic distribution of obliquity. So that's the prediction. So here I summarize the probabilities of terrestrial planets formed by giant impacts. So about the mass, so we derived the the scaling law of the large planets like Venus and Earth. So they are proportional to the total mass of embryos. And the typical outcome of the giant impact stage is two large planets and one or two leftover planetesimals, protoplanets. And they may correspond to Mercury and Mars. So about the orbital elements, so eccentric inclination is 0.1, so typical value is higher than those of Venus and Earth. So we need some damping after the completion of the Venus and Mars. Maybe that's by the dynamical friction from the residual gas or debris formed by impacts. And spin parameters, the angular velocity is about the breakup velocity, so maybe 70% of the breakup velocity. And the obliquity distribution is isotropic, which means the typical spin axis is about 90, right? It's like Uranus in the solar system. Just let me briefly comment the extension of the standard scenario. So far, we talked about the standard scenario and maybe already a bit modified or extended. But this extension of the standard scenario is going on in many ways now. So here I summarize the very important assumptions of the standard scenario. So here we assume the continuous power law disk, except the ice line or snow line. And we assume in situ formation of planets. And we assume perfect accretion, so no disruption by collisions. And we assume building blocks, the typo here, kilometer-sized planetesimals. But these are very, highly idealized, right? But now, for example, for this continuous power law disk, this one, so we are working on a discrete, discontinuous disk. So maybe formed by early disk evolution. And also many people are considering the radial migration of planets or planets during the formation. And also we have already heard from Nadal's talk, so not perfect accretion, but the collisional disruption and its effect on the composition is now taken into account. And also some people gave up to form planetesimals, but instead they use small pebbles as a main planet building materials. So in these ways, the standard scenario is modified and also extended today. So maybe, yeah, and the key process is the formation with correct solid-gas interaction in an evolving, not static disk, but in an evolving disk. I think it's very important. So sorry, I'm now running out of the time, and so this Grand TAC model we have already seen from the Nadal's talk, so I skipped this, and also, and I briefly comment this. So this Grand TAC model we've seen from the Nadal's talk is about the small mass and also the asteroid belt, the depletion of materials there, how to realize the depletion of planet building material there. But here, so we also propose this disk bump model. So due to the early evolution of the gas disk, we now find we can have this is the gas surface density. We can have pressure bump around 1 AU. And as we have already learned, this high pressure area can gather planetesimals here. So which can naturally lead to this formation of the localization of terrestrial planets. So here, this is radial distance and this is solid surface density. So initially, you can see this black planetesimal distribution. But along the gas disk evolution, so they just come to around this area, this very limited area. And then they accrete, they grow here to form terrestrial planets like our own terrestrial planets. But this is also an example of the extension of the standard disk model. Okay, so let me summarize my talk. So we discussed the standard scenario for the terrestrial planet formation. So where the building blocks are kilometer-sized rocky planetesimals. And it consists of 3 stages. The first one is dust to planetesimals. The second one is planetesimals to protoplanets or embryos. And the final one is protoplanets to planets. And the time scale is 10 to the 8 years. And so these are what we already, I already explained. So these not future, but present prospects. So in these ways, this standard scenario is now being extended and also modified. And also, let me note that, so we already found more diverse terrestrial planets in exoplanetary systems. So what we need to do now is we need to construct a model or scenario which can explain both the terrestrial planets in the solar system, but also in exoplanetary systems, maybe depending on the probabilities of protoplanetary disks. Okay, so this is the movie rendered from simulations we've already seen. So this is the sun and this is planetesimals, right? So here the size of planetesimals are exaggerated 500 times, otherwise we can't see them. So first we look at the runaway growth stage. So you can see some runaway growing bodies. And after about 1 million years, here. So this is the oligarchic growth stage. So you can see embryos. So we are now sitting on embryo. So here we have a gas component of the disk. So they are stable. I mean, orbitally stable. But on the time scale of 10 to 7 years, so this gas disperses. And now the final stage, giant impact stage. So look at this red embryo. So on this stage, we have a collision per a few million years. So then we switch to SPH simulations. So this case, they merge. So then we accelerate the evolution to see not individual bodies, but their orbits. So this expression we've already seen also. You can see some secular interaction between orbits. So then system evolves until it reaches some stable configuration. And then after 10 to the 8 years, so terrestrial planets are formed. Okay, that's all. Thank you.